also negative probability value and to use them to fuel our or to fuel local streams of quantum. And here is the list of non-classical aspects of quantum mechanics that I'm going to talk about today. There are the first two in my talk. So the first two lines, the coherence asymmetry entanglement and general quantum correlation, as you might research already. Entanglement is possible in computing. And but the last two is less known. Now this is this operation to popularize that is negative complex probability and this non-classical aspect of quantum mechanics has been shown as resulted in quantum cryptography, interpretation, computation, and so on. And in that they are also the key ingredients in quantum mechanics and quantum biology, which are the emerging fields in quantum science. And here's the plan of my talk. First, I will give you a summary of minimal quantum rules and the relations that are introduced to the talk so that they are eccentric. And then I use them to give you a brief introduction to models, asymmetric entanglement, and general quantum correlations, and proceed to introduce negative we are also as a possible activity and static value. And I deliberately divide the non-classical aspects into groups because they are showing somewhat different natures. Nevertheless, I will show the meaning of time. If I still have time, I will show that they are in fact closely linked or they are closely related. So I will use my remaining time to advertise my own work on using the negative and non-real KB possible aggregate value to quantify across problems and calculations. And if you want to know more about my work, and we start from minimal one rule. We know that the physical interpretation of quantum mechanics is a very difficult subject with no hope for near general consensus. But so you might incorporate different parts like correlation, and so on. But if you take that aside, then quantum mechanics is an operationally well-acted tool. So it gives us a very accurate rules and description to predict the probability of potential outcome in measurement, quantification, and transformation. So the rule of quantum mechanics basically gives us the description to describe what we do in experiment, which then converts into the rules of computation, transformation, and measurement. Let us start from the equation. In quantum mechanics, the equation transforms the classical data to quantum space described by vector in complex space or schematic flow in quantum space. So here is the cycle of operation. The left-hand side is input and the right side is the output. At the input, we have classical data, for example, push button there, and as an output, we get vector side K for state. But if our classical inputs are programmed, for example, select button play randomly for K, then we have an ensemble of pure state, side K, which occurs with capacity K, and if we do not have access to K, we have to average over all possible outputs so that we get this dynamic flow. And this is the mixed state. And let us take an orthogonal versions of the state, and there are infinitely many orthogonal vectors. Even so, there are infinitely many caches even for two-dimensional of probability. Then the states can be written like this, where this guy here, this thing here is just the wave function of the amplitude, and this is just the and next is the state transformation. In quantum mechanics, the state transformation transform state to another state. And the closed system that is described by a unitary operator satisfying this condition. So this is the symbol for state transformation, unitary operator, and input state, and the output is also the state. And if the state is pure, psi, then the rule for activating the state is like that. And if the state is not pure, represented by kinetic here, then the rule of activating the state is like this. Then unitary operator also transform an orthogonal basis of unitary space into another orthogonal. And finally, we come to the last rule, that is measurement. And here we talk about projective measurement. And the projective measurement is described by the set of plane one projector and this. So like collections of projectors, and here I use this pi x as shorthand for the projector, and it has to be orthogonal and results are. So this is the symbol for measurement. The input is state here, and as the output, there are two kinds of outputs. The first output is bicycle data, that is measurement outcome, and it is described by the one group. Here, this is the one group, and the second output is quantum data. So if the object that we measure survives the measurement process, then the state is updated. And the state post measurement is the rule for state post measurement is given by this quantum rule. So if we get the outcome x, then we have been made a selective measure to that. But if we don't get the outcome x, then we have to average over our post measurement outcome and the state update rule is given. And want to use these three rules to discuss the non-classical aspect of quantum mechanics, starts from coherence. And to illustrate to give you illustration, the difference between coherent and coherent states, we consider the following figure simply. So we prepare at zero and apply Hadamard gate and then make measurement of sigma c, which is described by this projector of 0 and 1. And in the middle here, the state becomes like that, which is just a superposition of the element of pressure 0, 1. And this is an example of coherent state. And then, at the end of the measurement, the state becomes 0, at 0 with probability half, and at 1 with probability half, so that if we don't keep the record of the measurement, then we have to take average over all possible measurements, and the state becomes like that. And this is just an incoherent or classical picture of the one. This is an example of coherent state. So now you know the difference between this is the coherence proportion, the element of the vector, and that is equivalent of a classical statistical picture of the element of the basis. And note that while that class is a coherence proportion of the element of the basis, but is not a coherence proportion of the basis plus minus. So it is not coherent with respect to this basis. So coherence is actually taken in concept. And let us generalize this concept to any finite dimension of the space. So we have to pick up, or we have to choose a reference space because coherence is batches definitely exact, and we'll have the reference batches like that. K running from 0 to T-1, where T is the dimension of the batch space. And as definition, a state flow is incoherent relative to the reference batches K. It can be prepared as classical statistical mixture of elements of the reference batches. So something like this. As the classical data, this is the preparation of the price. As the input, we input classical data prepare fact K, the element of the reference batches with product K, and we can ensemble of element of the reference batches at K, we can provide with the K. It's a closed so that the time schematic look like that. So an incoherent state can always be written like this. This is the definition of incoherent state. So it is a classical statistical mixture of the element of the batch. And because that the states must commute with pi k is the vector associated element. So it commutes with the pi for. And what about coherent states? Totally incoherent states look like this. So it is a classical statistical mixture of all the elements of different states. When mixing compatibility is uniform, we can find one of it. What about coherent state? Coherent state is just state that is not incoherent. So as formal definition, a state rho is coherent relative to the reference batch. Okay, if it cannot be prepared, so that is cannot be prepared, as a statistical mixture or classical mixture of elements of the batch. So since this kind of preparation leads to that incoherent state, like that, then a state is coherent when it cannot be composed like that, so it has to satisfy this structure. And therefore, there are some K when the states and pi K just not. And the maximally coherent state has the following one, so it is in the full weight proportion of the elements of the batch. And as an example, we consider a qubit system. On that, general incoherent qubit state is classical statistics of the element of the batch. So that's the following form where alpha squared, beta squared, which is 1. And if you write it or express it in terms of mathematics, it's active, and you see that the off-diagonal terms are all packaging. And as an example of coherent qubit state, we consider that qubit states where alpha and beta, alpha or beta cannot be vanishing, and the time schematic looks like that, or the time schematic looks like this, and time schematic looks like that. And you see that the superposition or the interference here in the object of the time schematic. And now we come to the second non-partial concept that I want to talk about, that is the concept of asymmetry. And to do that, I want to consider a quantum parameter estimation scheme we are in that reading. So suppose you have an object with properties like theta, and theta parameterized u theta unitary number. And the goal is to estimate theta fundamentally. And to do that, you send a probe one object, and after passing through the object, your state is updated like that. So now your state is parameterized by data parameter that will estimate. And to do the estimation, we have to take all possible measurements of psi data, and from the outcome of measurement, you use the classical explanation theory or methods to estimate data. Now suppose that u theta, this is parameterized by data, has the following form. So it is generated by sigma c of all. And and suppose that the invariant probe, suppose that probe is invariant with respect to the passage 01. Then after passing through the object, then the state on this the final state is equal to the initial state. So in this case, there is no increasing of the invariant state. Invariant states relative to the element relative to the passage 01 are invariant because the final state is the same as the initial state. And that's metric. This is the definition of metric. With respect to the unitary representation file on sequence. So semantic states cannot be used to increase data, and the usual spoil dimension. And arithmetic state is necessary. Therefore, arithmetic state is necessary result for quantum methodology. Now, let us generalize this for any finite dimension of the state. So we have to choose a Hessian operator that assumes that it has spectral equals like that. K here, small k is Hamilton K. Then it generates one parameter calculation like that. Then as definition, the state rho is symmetric if the translation unit that is requiring K, Hamilton K. If it is invariant with respect to the unitary translation. So this is the definition of symmetric state. In this case, the state and the generator of the translation unitary must compute. And since they compute, they share a common eigenprojectors, so the state can be like that. And this is just definition of modern state. And conversely, if the state is arithmetic, it does not satisfy it. So the state after the unitary translation is not the same as the initial state, then the state must not publish the initial translation, and therefore the state cannot be expressed like this. So that has to satisfy this condition. But this is just the definition of following. So the state is arithmetic with respect to the unitary translation generated by A, if it is common relative to the eigenvalues of A, the generator of. Now we come to the next non-classical aspect of entangled states. And to do that, we consider and bipartite states. So we consider two agents, Alice and Bob, and they can communicate as when we say and but otherwise they are specially separated. So the Alice can only do the operations on the system, and likewise Bob can also operation of this subsystem. And then Alice locally prepares a few states psi and Bob was Qiskit and Bob prepares psi b. So like this. And this kind of operation is called as, or this kind of procedure is called as local operation associated with classical quantification. And the resulting state is just a few states. So if you do local operation as a class communication, then and if it has a few states, then this is the state that this is the definition of unentangled or factorized few states. So as definition, if bipartite state is entangled, then they non-factorized or non-unfactorized. If it is non-factorized, so has to do that. This is the finest example of entangled state. So pure state is entangled if it cannot be declared by alloys because that using alloys alone will always factorize classical or independent state. So independent state, and let us generalize this for any generic state. So then you have Alice and Bob. They can communicate flexibly, but otherwise they can have local operations on their own computer. And now, as a general FOCC or local operation, assisted in flexible communication, Alice samplers the net from alphabet K itself, alphabet K, and each occurs with probability K, and tells the outcome before. And based on the outcome of sampling, Alice with the stage AP and what with the stage A. So the resulting state is simply written like this. So this is the definition of cyclical or undynamic state for generic state. So as a definition, bipartite state is inaccurate. It cannot be written like that. It has to satisfy this condition. And this equation to all cyclical states, that can be defined by algorithms, we have no quantum correlation. And you might think that since the state is cyclical, then it must not have any quantum correlation. It must be the answer. Once the expression we have to for the state to find what we mean by classical state. Can we consider engines, Alice and Bob? They can communicate classically, but otherwise they can only make local description like that. But given sampling K with probability K, now Alice becomes one of the elements of the basis of the unit space associated system. So Alice can only be private, which is one of the elements of the basis of the unit space of the system that owned by Alice. And Bob can do anything. I mean, can prepare any state that you like. So this kind of state, this kind of procedure gives you this state. And the state is called a classical equivalent state. And why we call it like that? Because there is a non-selective action on RTA on any side that is described by this set of protectors, which does not change the global state. So the state after the maximum is the same as the state before maximum. And this complies with our illusion about classical state, because classical mechanics we can always make measurement that does not disturb the state. And this definition of classical equivalent states leads to the definition of general quantum correlation, namely separable mixed states which nevertheless has non-classical correlation. So it is separable, but nevertheless has non-classical correlation. So as for a definition of mixed separable state, mixed separable bipartite state is inside classically or non-classically or quantumly correlated if it satisfies that condition. And why the name? Because if your state satisfies the condition, then any local projective measurement on A side unavoidably disturbs the local state. So this is the state pattern measurement, which is always not the same as the initial state for any local projective measurement. This is interesting because the state is cyclical, and the measurement is local. You undertake measurement on any side, but nevertheless, the local measurement on cyclical state nevertheless change the local state. So the local measurement thing, the local state is 5 to 5 state. And that kind of state, if your state looks like that, then the state one not commutative this protectors for any K and for any local detection. And now we come to the another non-classical aspect of quantum mechanics, which is captured by the non-cycle probability. We can consider quantum system in analytic dimension space and choose a value for orthogonal classes X and Y of two-time space, and as for definition, the period of any possible probability associated with quantum state rho relative to a value of classes X and Y is defined as follows. And why we call it probability or quasi-probability? Why we use quasi-probability or the term probability? Because it gives you correct marginal probability, and then you start of one of the variables. So if you start over X, then you get the correct probability of Y. This is usual probability, or real and non-value normal. And moreover, the KD quasi-probability also is also normal. So KD quasi-probability can be seen as quantum analog of classical or joint baseless probability distribution in the classical quantum mechanics. You know that in quantum mechanics, we are not allowed to define joint probability of two variables if the measurements corresponding to the two variables do not come. And using this KD quasi-probability, we are somewhat allowed to do that, but there is of course bias. The bias is that the KD quasi-probability may assume complex values and will scale part, also called as TMH or balancing of real quasi-probability, mainly negative. And these non-classical values known as non-conductivity. And then that if this condition, one of these conditions, why then the KD quasi-probability is real and non-negative for the usual convention of classical probability. So, and KD quasi-probability and its anomalous values personally enjoy the vital of the facts because there is more than many areas of quantum science and technology like quantum thermodynamics, methods, events method, and so on. As an example of KD quasi-probability, we consider a single qubit pure state like that, which is maximally correlated back to the axis 0 and 1. And as for the first status, for defining the KD quasi-probability, we say 0 and 1, and the second status is y plus y minus, the y plus minus is defined like that. Then, if you compute the KD quasi-probability and express it in form of matrix where the rows correspond to X and columns correspond to Y, then the matrix is on here. And as a second simple example, we consider this, consider two qubit pure state, which is maximally coherent. And as the first status, you take this, second status, you take that, the plus minus defined as usual like that. Then the KD quasi-probability becomes real plus negative. And well, I have said that non-commutativity manifests the anomalous values of the negative and non-reality of KD quasi-probability necessary. Non-commutativity is necessary but not sufficient. And you can look for another example in that paper. And recently I have shown that I have defined a sufficient condition for the non-reality of the KD quasi-probability. So if you can show that this is non-negative or non-anything, then the KD quasi-probability must be non-real. And it's the same similar subject condition and also the same to guarantee the non-reality and negativity of the And I would like to promote the KD quasi-probability and its anomalous values as a network for the polarization. So the KD quasi-probability gives you an informationally complete representation of states. So if you This means that if you know the KD positive vocabulary, then you can start scripting like that. And this gives rise to a big equation, which is my favorite equation last few years. And then how does the anomalous values of KD positive vocabulary on the negative and on the non-real values of KD positive vocabulary involve non-classical aspects of quantum state subjected to measurements such as poised, asymmetry, quantum uncertainty, and so on. And then this is the last aspect, non-classical aspect of mechanics that I'm talking today, and that is about staying in big values. So we have to start with what we mean by big values. As for the definition, the big value of a Hamiltonian operator K is selected state represented by density operator O, and positive state represented by the factor of Y is defined as follows. This is the mathematical definition. And if the state is pure, and this is given by one of the agent projectors of A, the Hamiltonian operator, corresponding to the agent value A, then the big value is just equal to the agent value. So in this specific case, the big value is just the standard set that you obtain maximum. And however, if you average over the probability to get Y, so this is the big value and this is the probability to get Y, then you get the usual quantum expectation value of A in state rho. And this this formula suggests that this term here can be seen as the quantum analog of conditional expectation value K given the selection Y. And you know that in quantum mechanics you are not allowed to define expectation value of variable given another variable if the maximum associated with the variables are not commutative. So using the concept of big value, we somehow to do that, but again, we realize that the big value may be non-real, and it may take values that lie outside the range of the agent values. Okay, and this kind of value is called big value. And while the big value contains complex numbers, it can in fact be measured or estimated in experiment. For example, using big measurement with force selection. So we consider the big measurement of a operator K with pre-selected state rho and force selected state F Y, and you can see the following procedure where the upper line there is the line for the pointer of the measuring point, and the lower line is for the system, and the system and the pointer are measuring point direct via this one dimensional track where P here is connected and G is the common constant. And we make force selection here and make usual strong measurement of the pointer, position measurement of the pointer. Then sub-measurement is called big if G is coupling between the system and the pointer, or if the initial state of the pointer is absolutely good, so that they also the agent values of K. And using this scheme, then we can infer the real part of the big value from the average portion of the pointer, and the imaginary part appears in the average value of the pointer momentum. And there are other schemes to estimate big value. And say big value, then where big value then is complex or that lie outside of the load range values of load range of the agent values of K. Place between model and configuration, model needs and the big value can be used to activate the KD positive value. Then consider the big value of phi H, a project of the pre-selected state, rho and positive state, Y, and big value can be calculated as follows. We've seen that the the numerator is just the KD quasi probability, and the denominator is just the probability applied. And this reminds you to the definition of unconditional probability. If you consider the KD quasi probability as the Yusrul probability, then this is just the definition of conditional probability of X and Y. That's why this quantity that we apply can be seen as the conditional KD quasi probability. It's one analog of the conditional classical probability. And again, in quantum mechanics, we are not allowed to define a conditional probability of one variable given another variable if the maximum associated with two variables are not. And using this definition, we can somehow define that conditional probability, but again, the price that the conditional KD quasi probability may assume complex number of intelligence. And if we arrange this like this, then you can see that estimate the KD quasi probability, we can just estimate the big value of the vector application, the conditioning experiment, and multiply by the probability applied. And from this, you know that the anomalous values of KD quasi probability and the negative or the complex values of the KD quasi probability correspond to these dimensions. And this is the criteria of how much? You have 15 minutes. 15 minutes. Okay. This is the technique of my advertisement of my own of our own works. And the KD quasi probability that I discussed in the previous slide to access or to characterize coherence. And given that I define the KD non-reality coherence in states relative to reference spaces as the maximum of the non-reality of the KD coherence. So that I take the imaginary KD quasi probability, take the calculus sum over all the angles and maximize over all the possible vectors of the space. And to manipulate that, if you input definition of the KD quasi probability, then you get this line. So that quantity there, somehow quantifies the non-commutativity between the states and the vector on the different spaces. And maximization is often assigned for orthogonal vectors of the different space. And that formula looks like complicated, but in fact, for a single QP, you can give it analytically, or you have to approach this formula. And for example, if the reference vectors is greater than 1, then you get this. And you see that the off-diagonal terms of the magnet appears here. So it gives me confidence to elaborate if this quantity that I just find can be used to quantify or characterize volume. And in fact, the quantity that I just KD non-reality coherence, it possesses certain cyclic properties for coherence quantified. And then that is kind of saying if analytically state is involved respect to the first passage, unitary covariance, and then that you rotate the state and the difference that is in the same unitary method, then the result is the same as if not rotated. And complexity and the mixing, classical mixing will reduce the coherence and not increasing on the partial phase, not increasing on the coherence operation, and not increasing on the stochastic phase of elements. And instead of using only the non-reality, we also propose to use the non-reality and negativity of the KD quasi probability to quantify coherence. So we define the KD non-classical coherence to quantify coherence relative to the orthogonal vectors A it actually quantifies the maximum total non-reality and the total negativity of HCl of the non-reality and the negativity, which is called non-classical factor. And you can also assume that it has on the desirable properties of the any non-reality columns that I just mentioned previous slide, so that it can be used as a way to quantify the volume. And we compare the two quantities with the most popular quantity to quantify volumes, namely L1 non-volumes, defined like that. It can compute the output of empty matter. And we attach it for single qubit. It blocks state like that, so the empty matter looks like this. And this is the plots of our numerical calculation. And you see that the three quantities, namely the two quantities that I propose here, and this L1 non-volume, they share similar quantitative features. Namely, that their finite state in this case is incongruent. Their finite state is incongruent, and they take maximum value for maximum equivalent state. And although they decrease in the purity of the state are decreased, or is decreased, which is expected in this case. Then I want to use the non-reality on the anomalous values, and more specifically the non-reality of the KD quasi-probability to quantify and characterize general quantum correlation or non-classical concept that I have used slides before. And to do that, we first have to define KD quasi-probability as an orthogonal product classes. So we have used product classes. So we consider a bipartite system, A is product connection, and we take a pair of orthogonal product classes. This is the difference of product classes. So A1 here is the orthogonal classes of party A, and B1 is the first classes of party B. And the second classes is the second orthogonal product classes states. Then the KD quasi-probability associated with the bipartite state rho AB relative to the pair of the orthogonal product classes X's is defined like that. This is the Yusrul definition. And I also define three variables KD quasi-probability by summing over one of the variables. For example, if we sum over V1, then we get this definition of the three variables KD quasi-probability. And both KD quasi-probability, so the four variables and the three variables KD quasi-probability would have correct marginal probabilities and normalize like the usual classical probability, but nevertheless they assume complex values and they report that this is the anomalous values of the KD quasi-probability. Then I use the non-reality of the KD quasi-probability to find or to characterize the A-side general quantum correlation. So I find this one limit we call A-side really non-reality. So we could take the imaginary part of the three variables, take quasi-probability, take the absolute value and sum over all the angles, and now we maximize over all possible orthogonal product classes of the space and minimize over the orthogonal classes of the space of A of party A. And if you manipulate, if you insert the definition of the A quasi-probability, then finally you get this plus line. So you see that this quantity quantifies the non-commutativity between the local state and this local measurement. So the insight is that the general quantum correlation should manifest into the anomalous values of the KD quasi-probability when the defining edges are at the product edge. And And for pure state, and if you look at this formula, it looks like very complicated. But for pure state, this can in fact be evaluated to get a closed formula. So, well, consider a pure state. First we make a position like that. Alpha k, that is discrete coefficients, and this is the two density operator of A. Then you finally you will get this one in terms of the reduced density operator of A. And if you use the and this and if you use the composition here, then finally you get this in terms of this coefficient. And this is just an entanglement monocle. So for pure states, the KD non-reality correlation that we find is equal to entanglement monocle. And because it for a two pure state, it has the following Smith composition, and the result is this, and if we plot it, we get this. So you see that if alpha is vanishing or equal to 1, then the general correlation is vanishing because in that case the state is a product. And if alpha is equal to 1 over square root of 2, then it takes maximum value, and in that case the pure state is maximally value. And this is example of separable state which nevertheless has non-vanishing general quantum correlation. So we take two Willis states, and it is known that for Willis states, when V is less than 1 over 3, then it is separable, but nevertheless, if we compute the KD non-reality general correlation, it is not factor. Now we come to the last part of our talk, namely direct estimation of non-classicality of quantum quantifier, direct estimation of non-classicality quantifier. Within that, we have to clarify what we mean by direct, by comparative indirect, what we mean by direct approach. In direct approach, we make a full statement of the calculated and use it to compute quantumness, say partial computation. But the drawbacks of this approach is that it does not tell you the operation meaning and also the nature, or maybe the nature of quantum is being quantified. Moreover, the number of the measurements is the size of the system. And in direct approach, we want to have a quantifier of quantumness which can be translated directly to operations in laboratory. And the benefit of this approach is that it tells us the operation meaning directly and given more information to the meaning of the quantum being quantified, and also may offer more efficient investigation. And here is a general scheme for that definition of KD non-reality formula and correlation that I have to go through the slides. First, we have a quantum sequence as in the KD quantum capacity of each value. Again, as the input of this quantum sequence is the unknown quantum state, that unknown quantum object, unknown state of quantum object that we are interested in, and also the first phases and the second phases. So we have to also have sequence that prepare these phases from the standard phases C. And these phases are parameterized by lambda x and lambda y. And as the output of this quantum sequence is the binary part of the big part probability, the real part, and we send them to the classical computer, and we ask the classical computer by using classical computation whether it is optimized or not. If it is optimized, then we get the KD non-reality or KD non-reality correlation. And if not, then we have to update the parameters and side effect to anthropic on these gases, and so on and so forth, so that until we get the 100% values. And if you learn about the control that has been mentioned by Professor, then this kind of thing is just quantum classical calculus. Then as for the quantum circuit that measures the value, recently, there are a few different methods, right? And recently there is a growing interest for schemes of estimating the value without big measurement and for selection. And example like that is one given here, proposed by Hanna et al. And they use auto swaps to estimate the big value. So it's very simple. You can take a very instant that the real part of the daily quasi-probability can be inferred by looking at the probability of 0 and the magnitude of the inferred by looking at the probability of 1. And there are other schemes, for example, recently Philip and Simona themselves proposed another scheme which does not depend, efficiency does not depend on the dimension of the reference space. And as for the quantum circuits for rotating patches, and for single digit just like simple, if you want to rotate the patches to one any other patches in the closed field, then the unitary phase will confirm when the patches that one can be parameterized like that, so that the unitary matrix that rotates on patches which is like this, and it can be decomposed like that. So we have the following circuit. And this is the on top. So the take-home message of my presentation is that the non-functional aspect of quantum mechanics has been identified and exploited as resources for quantum technology as real as energy. So it is important to deeply understand the defining non-classical features like dynamics, for example, of quantum mechanics to define simple states of quantum technology. And as for the advertisement, I would like to promote anomalous KD possible probability and link value as a very rich defined complex framework that understand different forms of platform. Thank you very much for your time.
Okay, thank you very much, Dr. Agung, for the very nice talk. So, question please for Dr. Agung. Sorry, thank you for this very interesting talk. I just have one question. You said that the maybe what is probability is faithful for quantifying coherence.
The animal cells on the non-reality on the negative probability. If you maximize over one of the defining gases, then it is quantifying coherence relative to the other defining. But any quasi-probability alone is not sufficient. If any quasi-probability is positive or real and non-negative, then it says that there is no coherence.
Why do you what is your main motivation why you use this probability while the other researcher already use something like with function or function and others for many function for measuring the non-classicality and that thing.
But of course, many researchers use Wigner functions, especially quantum optics. The field quantum optics, they use Wigner functions. So the negativity is can be used to identify some part of quantumness. But there is difficulty to extend Wigner function to finite dimensional space. So if you want to quantify the coherence of Qubit system, then you have to extend the function finite. And there is difficulty in that, but there is what the proposal to that. And people working in quantum computation have shown that big negativity for finite dimensions can be used to characterize quantum speed up. So negativity, some people argue that negativity is a necessary, if not negative, it's a necessary condition for quantum speed up. And the reason I use any quasi-probability is because it is very natural in finite dimension. It's very natural in finite dimension, and as I mentioned in the slide, any quasi-probability gives you an equivalent information about the quantum state. So, so the stupid question is that how does the negative quasi-probability encode this non-classical aspect that are usually encode quantum state in negative quasi-probability? So, what features of any quasi-probability shows quantum? That is my main motivation. So let me repeat it again. So my main point is that any quasi-probability is equivalent to the state, and we know that the state shows non-classical aspect of the element, and why and how does this any quasi-probability proceed?
Okay, more question? Yes. Yeah, maybe another stupid question. I just wonder, you mentioned about for non-classical aspect. Is it necessary for us to fulfill all for those non-classical aspects to create one quantum system, or we can utilize only one aspect?
Yeah.
Thank you.
I guess all quantum technology requires some form of coherence. Coherence is necessary for all forms of quantum technology. There is no coherence with respect to some factors, then you cannot do quantum mechanics and create quantum technology. But for example, I don't think that some aspects or all of the aspects are required for the functioning of certain quantum technology. So I guess I think that certain schemes of quantum technology require some certain aspect of quantum technology. But it is always interesting to better understand the relation between these non-classical aspects.
So you mentioned that coherence is the main ingredient, right?
Yeah, I think coherence is the prerequisite for all of these. Because otherwise, there's no proportion and there's no quantum mechanics.
So I was wondering earlier on where the people here going to that L1. I hope that.
Yeah, I can work that.
You know, you're always like L1. One of the for the measure really because that also that environment.
Very difficult question. But one of my point why I use KB quasi-probability because as I argued in the last slide, we don't need to know the state beforehand. I mean, if you want to use L1 on coherence, then you have to know the state, you have to make the traffic, and then calculate the complex and so forth. And if by using KB coherence, then I can use this schemes for estimating big value without knowing the state beforehand, and then it gives you the coherence. And also, if I can do that, then I can guarantee that it is L1 quality for all of them. So the science gain columns is weakness for L1.
So another question is that in the last slide where you had the first case, the formula that you do is the state size.
That I have not checked yet. I have to check it.
Can you say anything about how to analyze it?
Yeah, that's again is very difficult question. So my next goal is to extend the comparison to multi-power and for example, and also to find like channel volume or channel asymmetry or set volume. So that's why I said that it is a lot of
Just a funny comment. Your equation seems to say that now to understand quantum mechanics is not only.
or if you think that you know yourself, you don't know quantum mechanics, or if you think that you know quantum mechanics, you don't know yourself.
Okay, thank you. Let's have some questions from online audience. The first one is, what is the difference between selective and non-selective measurement?
Okay. By selective measurement, you basically record the outcome of measurement. So, if you get, for example, outcome X, then and you record it, register it, and keep it, then that is selective measurement. But by non-selective measurement, you erase the information or data, so that you have to average all possible measurements. That is excellent.
Okay. Yeah, from student? Yes. I would like to ask, what are the advantages of having the probability for maybe progressing or technology? Is there a probability of selective or
Recently, there is previous this paper, and this paper also motivated me to study the quantum. This paper by I didn't put it in math, right? This paper by and they show that they get a k probability or some generalization of k probability can be used to enhance decision is certain on the road. So this is full of on the road. But of course there are many other roles of negative probability. For example, one thermodynamics want to extend the definition of work, and one of the way to do that is to lower the probability. So there are many roles of animal science.
Okay, let's give applause to the crowd. Okay, so now we have lunch until 1 o'clock. So the next section, which is hands-on simulation using the Qiskit by Yusrul, will be start at 1 o'clock hour. So, okay, enjoy the lunch break.
Gimana? Iya. Iya pakai laptop sendiri maksudnya. Gak nyampe. Potong nggak sih, Pak? Ini kayak kepotong nggak sih? Oh gitu.
Nggak bisa langsung ke Yusrul aja. Maksudnya seperti itu. Tapi nanti aja. Nanti aja. Mau sampai kan?
Sampai sini. Oh sekarang. Kalau sini kosong nggak sini? Apa? Oh gitu. Oh ya. Ini cepet gak apa-apa?
Ini masih nyambung ke sini, kamu butuh apa?
Enggak, ini kan aku dapat yang panjang.
Oh, kok jalan nggak?
Main nyoba. Hah? Tapi beda sini. Nggak bisa depan ya?
Oh, kamu pengen jauh ke depan? Ya udah coba skip, cabut aja.
Lewat sini apa aja?
Terus partainya kan, benar nggak ini pasti depan kan produk depan. Oh, jawab itu.
Mungkin BRIN bisa jadinya teori untuk kekurangan tadi. Yusrul tadi ya. Oh itu tuh tadi.
Yusrulnya makan ini nggak mau tuang lagi. Wah.
Maksudnya masih sama kan ya? Maksudnya mau kasih ke Yusrul.
Bro. Izinkan hamba untuk share screen yang mulia. Yang mulia, izinkan hamba untuk share screen. Sudah? Belum nyanyi?
Iya.
Kalau udah nyanyi boleh.
bagus jadi.
Harus banyak ini dokumentasi.
Ada yang pernapasan lu, biar nggak tegang.
Oh, itu meditating.
Nas, aku liatin kan. Ini lagi aku.
Apa? Kamu?
Liatin kan.
Beli apa? Gabung apa?
Kalau ada apa-apa,
Kalau belum event resmi, ini kota diambil letter lah. Kalau udah event resmi, udah mulai baru. Kalau belum dimulai, ya letter lah.
Good afternoon, everyone. Everybody already going to this room. Yeah, maybe we will start the afternoon session. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. My name is Yusrul. I will be moderator for this afternoon session. And welcome back to Indonesia-APCTP workshop on quantum computing and simulation. In this afternoon, we will have a hands-on session using Qiskit. Qiskit is one of the SDK software development kit for working with quantum computer. Actually, we will use Qiskit on our laptop just for simulation, but in the real system, because Qiskit is big like IBM. IBM is one of the company who can make quantum computer, and you can use Qiskit in the real supercomputer, real quantum computer using IBM. And today, Mr. Yusrul here, we will demonstrate how to use Qiskit on your own laptop and also on the IBM quantum computer. And okay, firstly I will introduce the speaker, and Mr. Yusrul, Hanna is a researcher from BRIN Research Center for quantum physics. Okay, maybe before we start the hands-on, maybe everybody will better to get your own laptop, and maybe Mr. Yusrul will guide you how to install and prepare the hands-on. Maybe Mr. Yusrul will can start the workshop.
So, thank you, Dr. Edi. Good afternoon, everyone. My name is Yusrul Hanna. So, today we will learn together about how to simulate quantum computing using Qiskit in the first day. And the second day, we will learn together how to simulate quantum chemistry using quantum circuit, but and using PDLAM. The two devices have a different configuration. In IBM, only configure with superconducting qubit, but in tomorrow we will learn about how to simulate PDLAM based on the photonic configuration. So there's two different configuration, but yes, different configuration give some noise and some error. So okay, before we go further about how to simulate quantum computing using Qiskit, but all of you please jump into my GitHub. It's my Hanna. So please, if you have infinite, please go to in the quantum research ID. So in the yes, this program book and support material, please click this link. So you will find some link to direct to my GitHub. Okay. This one, you can copy it, and if you are closely using a GitHub, you can find my GitHub.
Open apa?
Tutorial hands-on. So today we have long enough to simulate quantum computing up to 2 hours. So we have to maybe slow pace. If you have encounter any problem, please raise your hand. So the first one is okay. If your laptop is don't install any some program like Conda or Visual Studio Code, please install first. But not only limited to 3 programs, you can use you can use quantum Google Collects is not a problem. So please. If your computer does not support to this install this program, please using Google Colab. Please Google Colab to install. But if your laptop is installed by Linux OS, such as Ubuntu, Debian, and etc., please follow this guide to install Jupyter Notebook, because why I guess you are using Jupyter Notebook is very friendly, and we can provide some note in the notebook.
I will add information because Qiskit is written in Python language, so you need to install Python first. Python is one of the most popular programming language, I think. And after that, we use Jupyter Lab to find graphical interface or solve the problem.
Okay, so maybe I will give you some 15 minutes. Then I will 15 minutes to install some program I have provided. So please choose one of them. After that, we are going to jump into the real simulation about how to construct quantum circuit first with a 1 qubit and 1 qubit and so on and so on. And also we try to declare some gate with the different configuration. And then the last, maybe if I have the time, I will give you how to implement a quantum computing in the real system using those involved many body embedding system like this one. Okay.
Just to make sure, so when we use Google Colab, you don't need to do any of this installation, right?
Yes, of course. But you have to install Qiskit maybe after locally.
Oh, okay, but from Google Colab.
Yes, if install using any Google Colabs.
We have to use the real platform.
Not necessary. You can use Windows, Ubuntu, or anything else in my house. Maybe. If you can encounter some problem, please raise your hand. How to have problem with installation first. Platform platform and Coda, Mini Coda, or Visual Studio Code, and install some all of these. Install Jupyter, Mobile, and Public, and we have you Linux operating system. Please follow this command. But you are using Mac OS, please. I think Mac OS have to follow the OS.
everyone done the installation for Jupyter Web and Visual Studio Code? You already installed in your laptop? Yeah, please, if somebody have problem, please raise your hand. Maybe I will go around to probably in bahasa Indonesia.
Maybe just suggestion, let's try for, I don't know, and we probably have it still stuck in some talent and then just use the wallet.
Maybe can you demonstrate how to use the wallet? Okay. So if you have some encountered problem with your installation, encoder, minicoder, Visual Studio Code, and anything else, please using Google Colabs. So maybe we have jump into introduction of the quantum computing using Qiskit. So the first one is please all participants install follow this command. Follow this command first. This means install with this tool. In the Python, command is this one. If you comment. Please install this one. Okay. This means you have to install a Qiskit visualization in order to simulate visualization of the Qiskit, like the plot sphere simulation, and also plot histogram when we pass out the measurement of the system. And then the second one, we install Qiskit IBM runtime. This one is some model to interact with your local computer with the real system of IBM. So please don't not install this. So you already uninstall Qiskit, but maybe only this three some module you have to install. Install in Qiskit users, Qiskit IBM runtime, and then Qiskit visualization. After you have installed, so we could check installation first. Your Qiskit install very well in your computer and your Google Colabs. This one you recover it. This means that this code have to give explanation how version of Qiskit you have installed, like this Qiskit the newest version 0.40, and then using Qiskit Air is IBM provider. So, but in the part last, we have not installed because we have done first of the some machine learning in the quantum computing. But this tutorial only in basics to create some quantum computing and also interacting with the IBM quantum computing. Okay. So maybe I can continue. Do you have some problem to install this one?
Can you explain the third line? Can you explain once more the third line if installing Qiskit?
Third line, this one.
Yeah.
Yeah, third line, this one is only general some module to install in Qiskit, like how to running, executing some system and also construct some gates in the quantum circuit. So this is general, and we use it, but the two and top, this is installation to how to visualize the quantum computing results, such as measurement, block pair, and then the second is with IBM runtime. Only this module can give you interact with the real system of quantum computing. Okay, so these cells only give you some information the Qiskit you have installed in your local computer. This is very important because in the Qiskit every 3 months I think there are some version of the Qiskit. So between this version and the before version have a different configuration. So please take it. Okay. Okay. So before we create some quantum circuit, please write this code. This means import some quantum circuit, means like you have to declare some quantum circuit, and that means we have to interacting between your local computer in the IBM, but it's not a real system, but only in the Qiskit algorithm. And the execute, it means that your circuits compile with the Qiskit baseline. So this import numpy as numpy. This is numerical Python. So this is very important thing to import, and then auto visualize that Qiskit is publish program to give you some measurement result from the quantum circuit, and plot flow vector to give you some insight how to a step factor give you direction in the closed sphere. So okay. The next one is how do we get some step factor and plot coordinate. This one is some definition function how to calculate the quantum circuit. So we only call the step vector. So the Qiskit, it means that quantum circuit we have created, and display latex through this means that if you want to show the step vector in the latex representative, please set true. But if not, you can set false. Yes.
Better for maybe 1 minute for each line so that we can directly run in our computer.
Okay.
What do you think? Maybe from
I cannot hear you very clearly. Okay, so maybe display matrix means that if you have some quantum circuit you create it, and then you want to calculate only the state vector like eigenvector only. But if you want to display like text in maybe the next step, you can understand what this mean display like true and false. So state vector into LaTeX format, and you false not only in the LaTeX format but display in the NumPy format, NumPy in array. So two difference, I think is not very very strong problem. I think it's only about display and visualization. Okay. Okay. Maybe I want to I shall into what does mean of state vector module, sorry, definition function. So when you have a quantum circuit first, so you can call it in the slide Qiskit, and then Qiskit in the Qiskit there are many get back end the theoretical simulation like state vector, unitary simulation, and also QSM simulator. State vector simulator will give you some definition about a state vector, and then maybe after the next cell, I'll give you some how to define some unitary transformation of the quantum circuit. So this one, okay, we are using backend state vector simulator to obtain the some state vector, and also execute with the quantum circuit and backend, and then the result is mean that you pick up some result of your quantum computing only in state vector result. So this one. So this is get state vector only mean that you want to pick some state vector in the line. Okay. It is the second one is a block coordinate. This means that if you have some two coordinate, in a column vector, so you can visualize some block coordinate representative. So this means that if you have two state vector, you can visualize in the block space. Maybe if you a beginner of the using a Jupyter notebook, you can run it in the between cell in the shortcut using Shift Enter, or maybe in the top of the quantum Google collapse, you can run with this button. Okay.
How many qubits are we assuming in this equation?
In this tutorial, only 3 qubits. I mean 3 qubits, but maybe I jump into my real system. We can also determine the number of qubits under 6. But in real system, the real system, we have configuration up to 2057 in the real system. quantum again. But in this models only construct theoretic, not in real system. Okay, so how do you first to initiate the quantum circuit? We have you can use a quantum circuit. This means that you want to create some quantum circuit in the 1 qubit, 3 qubit, or anything else. Up to you. In this tutorial, I will give you some basic line. How do we define some quantum circuit only in 1 qubit? Oh, maybe so. Okay, this one. In the Qiskit, qubit represented by the line of wire. So this line is mean that what is does of the state vector representative is doing in the single qubit. Yeah, the single qubit is a state vector. This means like Dr. Nadia asked me, but what does happen when to display like true and false? The true this means that you have to display your state vector into latex. If you have any, if you maybe you have a sort of the artistic that this and you see it that your eyes is very your eyes and your soul is very happy. Maybe in the theoretical person. It's just only visualize.
That's for an exactly up state, right?
Yes.
Can you visualize some other state, right?
Okay.
Pointing towards some other state.
Yeah. Maybe the next time I will give you some point of another direction. So, okay. This one, when you put it the state vector of the quantum circuit, this one, you can get some state vector like this, 1, 0, and what about the block pair configuration? This means that block pair configuration give you some direction in the cat 0. This means that in the real system, in a Qiskit configuration, this default in cat 0. Please take a look at that. In the first configuration, the default in the real system it is initially with the cat 0. Cat 0 is made of 1, 1, 0. Yes? Oh yes. Please, maybe your laptop not install latex first. But if you don't install it, please, maybe you can change it for not this course.
Jadi yang di the GitHub is not updated. The first cell not showing the GitHub. So maybe for you have still has an error. If you can, or maybe you can update the GitHub. So if you go to Qiskit, go.
Yes. Oh yes, now. Yeah, maybe okay. It have maybe the hidden these two cells. So the problem the first please install this one. Maybe I'll give you some up to date of my Jupyter notebook. Maybe I will update my GitHub first. Do you have any comments? Okay. So, I am updating now in the my GitHub list. If you have enter some to install Air and anything else in the Qiskit platform, you can install this one first. And the second one is not necessary, but only to configure to give you some like that in Qiskit is import this version before. Wait. Maybe you have any some problem to install first, or I can continue my talk. Okay, there's no problem. Okay. Okay. So okay, maybe in your PC and your laptop does do not install yet LaTeX and occur some error. Please setting display LaTeX false and give you some step factor in the result of the QB if you want. So that means that when qubit do not add some gates, that I think it's the pure qubit. This give you some representative that in Qiskit initially with the gate 0. This means that 1 0 in up. If you have specified by speed up, and then what about when we flipping in the speed up to speed down or into get 1, you can use it initially introducing with the X gate, Pauli X gate. So Pauli X gate have some purpose to flipping the qubit. This one you can add some X gate. X this mean X gate, and 0 this mean that you introduce the qubit in the index 1. So in the maybe Python indexation is very different rather than in the other language. So in the Python first initially from the 0, not 1. So this means 0 in the mathematical method in 1. Okay. So if you calculate the state factor of this one, that means that when you introduce qubit with the X gate, that initially and spin up, flipping into a spin down. What about the visualize of the plus pair of the standard spin down? I can see that state factor going to direction and 1. Okay, you have some question? Okay. I will continue my talk. So, what about when we want to introduce a Hanna gate like this? So the Hanna gate, when we when we involve with the initial state, so that means that state factor is going to solve this state, and then to visualize that Hanna get that going to positive x direction. So this means that in the quantum computing literature, this means that when Hanna gets matrix when involved with the direct multiply with the get a zero, this means that represented by get plus. But when we apply a Hadamard gate in the get one, so it will give you some flipping in the this one. So the direction of the qubit, direction of the vector of the qubit going to x minus. So this means that in the theoretical, if you study quantum mechanics, so initially anything else about the quantum circuit configured with the get zero, anything else. So if you want to first initially with the in the get one, you have to using x gate first to flipping the 0 into 1, and in the quantum circuit theoretically it's very easy to understand. And if you anything else about the qubit, maybe the next one how to dealing with the another qubit, maybe 1, 2, 3, and maybe so on. And you have a 3 qubit. This means that initially with the zero state. Mean that you have involved this qubit. It means that zero connector product with a zero connector product with a zero. That means quantum computing it only gives you some representative zero. This means that the initially state is going up to 0 when you have dealing with the qubit. So this means it's only unitary matrix. So the next one, how to calculate a unitary matrix in the qubit. So in the sorry, but what it does mean or how to state factor is state factor configure how to calculate with from the states analytically. Step factor is when you have some p, maybe arbitrary state, is equal to some unitary matrix, anything else. Depends on the configure of the qubit. So it's only this one can multiply with the 0, or maybe you flip it in the one you get one. So this is you can change it. Okay. Maybe the next how to visualize the circuit. If you going with the MPL visualization like this is MPL format. So this is MPL. If you visualize quantum circuit, you can visualize with the MPL display like this. And when you have pouring with it, you can change with the text. Yeah, maybe it's like so some of the point of view you want. and you pour it again, you can fill it with the latex. So in the Qiskit, only three visualization of the quantum circuit using MPL, text, and also latex. If you're happy with the colors, you can using MPL, and then maybe you have maybe I have a simply person, yeah, you can use text. But if you like latex edits, yes, this one is very accommodated with your editing. This is but you're seeing. So when we try to construct some single qubit and multi-qubit asset vector, so this means that quantum circuit I declare with the 3 qubit, and every qubit I declare with the other one gate every qubit 1, qubit 2, and qubit 3. So we visualize the quantum circuit like this line. So what about the state vector of the quantum circuit configuration? This means you using latex, display latex. So you obtain that column matrix of the set vector after Kronecker program and multiply with the zero at zero. So what did that what that mean? So it's been like if you so what is that mean? In the quantum circuit, so the first one is especially defined by 0, 0, 0, because if in this tutorial we are dealing with the 3 qubits, so we show the 3 qubits 0, 0, 0 until configuration up to 1, 1, 1. So this one is 0, 0, 1. This means you have run it into this. So, and you can maybe this student confused how to represent it with state vector into this one. This one is I think this the same maybe the same results on the display. So if you're dealing with the 3 qubit, this means that we have to dealing with the maybe 8 qubit, 8 column and 8 row, because when you declare with the matrices of the qubit is only n, and this means that number of qubit when you using 3, so you have dealing with the 8 row and 8 column. Yes, 8 column and 8 row. So this means that 0, 0, 1 you have dealing with this one 1, 0, 0 until 0. So this is 0, 0, 0, 0, 0. Only this configuration. This means that 0, 0 means that we have initially with the first number of this qubit. So the representative we can using from the state vector into this configuration. This is only visualized your result. Okay. So we are dealing with the constant factor of the quantum circuit. What about when we try to determine some operators or unitary matrices from the circuit? So this one, and from Qiskit, in Qiskit is provide some module like operators. So in operator quantum circuit find, this quantum circuit find is mean that you have to calculate only in unitary matrices. So we have then that this means that is result of the unitary matrices in the configuration of the Hanna gets in the TQB. So they are 8 column and 8 row. You can see it. You can see it. So maybe another circuit. Okay, we are dealing with the quantum circuit 2 and the circuit 1. Sorry, in the quantum qubit 1 we have directed Hanna gates, and the second qubit we declare with the Qiskit. This one. How about the state vector of this configuration? We have obtained this one. And what about operators in the quantum circuit 6? This is quantum circuit 6. Because there are 2 gates and two qubit, you got some 4 column and 4 row in the matrices. So how to change the step vector to operator like cross product or okay, maybe this one I will give you some explanation how to change with it. Okay. When we dealing with the quantum circuit 1, so please remember that quantum circuit 1 there's no some gates I have declared. So what representative of the quantum circuit 1? This means and if you maybe if you don't declare any gates, something like this, yeah, example like this. This means that you're dealing with the identity matrix. This means known as identity matrix. How to calculate from the scratch on the analytically without some Qiskit platform? How to dealing with this? So if you have, maybe I'll give you a qubit. Okay. If you have a qubit and the qubit once you declare some Hanna gates, and in the qubit the qubit 1 you have a declare. And the qubit 2 you haven't declared anything about gates. This means that in Hanna gates parallel with the identity matrix. So how to calculate analytically without quantum platform? So you only this using connector product between qubit. So Hanna gates, I'll give you some operators symbol and connector product with identity matrix. So this means that when you have don't declare anything in the in the qubit, this means that identity matrix is going to in the qubit automatically. So this means that you calculate the operator of this area. This means that state vector in initial state and state vector in final state. So this is a unitary method that you have calculated with I think direct multiplier with the initial state. You got some final state vector of the configuration. Okay. So please don't confuse although maybe in quantum circuit the way. But if you have studied quantum physics, but only using matrices representative, and it is kind of the problem not really not really strong enough to. Maybe any question?
Yeah, question. What's the difference between state vector and the operator? Because in state vector we have in example 5, section 5, we have the current to the right, but in the operator it's like with the plus and minus the same value. So I don't know. I don't still get it. What the difference between those two?
Okay. So maybe I will repeat your question. If you have qubit type, it is.
In quantum secret type,
Oh yeah.
yeah.
Okay, this one.
Yeah, there. In state vector we have 8, like what is it? 8 columns, right?
Yeah.
Yeah. With the value of power 2 over 2. But in the operator, we have the same value, but there is plus or minus. And I still don't get what's the difference, but they have same value, but what's the difference here?
Difference between state vector and this one.
The bottom one, the operator.
Oh, the operator. Okay. So okay, please don't confuse. I have explained with you that operator, this means you calculate with it, okay, only with it. So operators only calculate some operation in this one, and then why this state vector? This means that okay, operator I got some minus, but when I have to calculate with the initially state vector, I got some only positive, right? Okay, so this means because you doing a direct, this maybe I give you some, okay, maybe this one I'm not correct all. Okay, this one, so okay, maybe I think minus. Okay, so step 1 is you initially with the 0. Okay, so 0 it means that okay, 1 0 0 0 0 0. Okay, okay. So this one is mean that you got dealing with the 0 0 0. Sorry, get 0 0. Okay. So what about when we try to move when this one move into jump into the below? This represented by 0 0 1. Okay. Okay. So the multiply between the matrices we change the direction. So we could obtain only like this. So
Yusrul, since you deal with 3 qubits, right? fact that your matrix size is 8 by 8, that means you deal with 3 qubits, right?
Correct.
Then I think you should be writing product of tensor product of 3 2 by 2 matrix.
Oh yes.
Not just 2.
Okay. So okay, maybe. Wait a second. Sorry, there's a difference. When you dealing with the qubits, I have a declarative qubit in Hanna case, parameter product in Hanna case, and Hanna case again, and we initial state. This means that initial state in your qubits initially with the 0 is again. And so you have in the representative of the initial state is 0, 0, 0. Okay.
So the circuit matrix that you are showing in here corresponds to this product. The product of 3 Hanna matrix.
Yes.
Yeah, that's why I was wondering if you have
Oh yeah.
Hanna and identity.
Oh, yeah.
That's impossible.
Okay. Thank you. Remind me. Okay. Maybe any question? Do you have any question? Have you confused? But take a note that this tutorial is only intro, not jump into the real system. So please, if you confused in the first part, please ask me. So went up. So
The initial state. Is that the initial state or the resulting state?
this one is resulting state, not initially. Initially, this means is yeah, up on it up. When you dealing with the down, you have to apply with the Qiskit first. So this initially quantum circuit in the state. Okay. If you confuse, please cut my talk. So raise your hand. Okay. Waiting for me to explain until at the end. Okay.
Is it speak louder or is the microphone?
So maybe I talk already. Anything else?
Sorry, where are we now? QC5, right?
Yeah.
Where are we now? QC5, right?
Yeah. QC5. But this is QC6. The unitary matrices, and then this one of the slide of the quantum circuit when we introduce Qiskit in the 1:2 in line.
I have a question though.
Yes.
As far as with the visualization with the block field, basically, it is just to show us how see the qubit
Okay.
can do a numerical calculation, right?
Yes.
I mean, there is no way of visualizing the state of 3 qubits in terms of something similar to block field.
This is a similar variable space. So in previous example, so we have a dealing with the only two value of the this one. Okay, this one only two. This means that and you fill it in the blocks block vector like this. Occur error. So please take it. Error please, because in the block vector we have to give three value in here, not only two but three. This means that three is angle of theta, pi, and also of r. Yes, you have in the spherical representative. So you have to three input to visualize a block vector. But in the day, today, I will give you why does only two value can simulate block vector, block space, because this one. So in the set vector one, I try to multiply by two. At least I change the representative of the Cartesian representative into spherical representative. But in the real system, if you dealing with the block space, please give three input. But when you are using my code, you put visualize only two input.
My question was actually about whether there's any way of visualizing the state of more than single input.
Okay.
Is there a way?
Maybe perhaps we could simulate with the block vector with not only with the 3 qubits, maybe and so on. So we are dealing with the real vector of the each system. So this one, okay, maybe I'll talk later about how to plot with the dealing with when you have multi-qubit gates. So not only one, but in 2 and 3 and so on. We can display that.
Already.
Yes, okay. Maybe after this, I'll give you Yusrul. So maybe this this tutorial, yeah, maybe it's lower and then up. So.
But basically, we can visualize.
Yes, basically we can visualize all of the state vector.
Yeah, so far you have shown us what you for what you are wondering how the visualization will work.
So okay, maybe the next step, maybe I'm not jump into 3 qubit, but okay, maybe either in the previous. Okay, we are using a quantum circuit 2. So this one. So this is the display of the quantum circuit. So first qubit I declare define some CNOT gate between qubit 1 into qubit 2 into qubit 1. So what about operator? So this operator of the quantum circuit, so unitary. This is so. This is only what about the state vector of the system? Here we a system. So how to visualize with the block vector? So in the block vector, maybe you have take a look this. In the state vectors, only I configure in real part of the system. So So this one is configuration only at the block space in the QB2. What about the
This is the visualization for 2 qubits?
yes, visualization of the qubits. Yes. So what about when we dealing with the 3 qubit with every qubit declared with the Hanna gates? So how to deal with the Qiskit will have the 3 qubits to simulate with the block vector. Which one? So this one is only configured with the real part, but if you delete this real part, so what's happened? Yes. What happened when we not dealing with the NumPy real? There's you have to face some complex warning. So this one is in the block vector give you some direction of the imaginary part. When you only configure the imaginary part, okay, there's nothing prosper in here. So probably the best part to deal with you have a more qubit like 3 qubit and so on and so on. Please add some np dot real. This means combine the reals only pick up the real value of the step vector. Okay.
So in this case, we don't need to verify the block coordinate. Okay. No, we don't need to.
We don't need to because in the Qiskit handle. So please maybe this please take a look at in the you want to visualize block pairs. Please give only 3 input. Only 3 input. This means that the block pairs only block pair.
Can you scroll up this? Down.
Okay. What it does mean? This is in the Qiskit we plot and Q-scan. Q-scan does mean that what about the configuration and phase of the block? This means that so in the block space maybe okay, maybe add one. So if you there's a way to write it here. Okay. So how to representative this means that the vectors representative into some cases data and exponential I pi plus sorry let's see. So this means configuring the state 0, and this one is configured in the in the step one. So if you have anything about the step 4 and 3 and 6, anything else, so this step vector gives you a configuration of the zero state, sorry, cat 0 and cat 1. Yeah, this is like a representative of the spherical coordinate.
That is for single qubit, right?
Yes,
So
we have.
we have 2 qubits. Don't we have two kinds of data, two kinds of parts, and then how do we visualize it?
Okay, so this means that yes, if you maybe this one is not only in a qubit one, but also and so on 2 and 3. So in a closed pair, step vector enforced into qubit representation, only one qubit representation with the theta and phi. So this means
For this, it is clear that we only have 2 bases.
yes.
But if we have 3 qubits, for instance, then we have 8 bases.
Yes.
Then how do we put the physics in front of each base?
So in eight bases, so maybe okay in the in the in the qubit state. So this one. I got it. Question of the so this one is only configured yes between it in one qubit representative. So if you dealing with the maybe 1, 2, and 3 qubit, so this means that you have different configurations. That means that if with 3 qubits, maybe you have dealing with 3 qubits. This means that you got some configuration close pair in the 000 and so on until sorry 111. So you have a representation of block, but you can use with the maybe I forgot to dealing with this. You can more
Is it that we somehow have to do vector addition?
yeah.
Like we do it in algebra, we do vector addition, then the resultant of 2 or 3 vectors will then translated into a big block field, a block field corresponding to the resulting sum of the qubit. I mean, is that the idea? So I mean the single arrow will correspond to
So there are only give you some one qubit representative, but if I have the how to simulate Okay, this one. This one is how to simulate every qubit with applying with the quantum circuit pipe configuration. So please remember that in the qubit pipe we declare other markets every each qubit. So this one of the visualize of a blocks for every qubit.
Yeah, but this one is not. If you have to visualize 3 qubit, I think in the same case, we have to examine the problem how to higher dimension than
Oh.
3D.
We can only visualize each qubit, but
Not the
for the whole qubit, it's like
yeah,
the problem of
sama kayak
viewing
kita
for
4 dimensi.
dimension.
Oh yes.
We can always visualize each qubit and display the 3 of them.
Yeah, 3 of them.
Yes.
But we are not seeing the relative basis in this case.
Yes. To determine the relative phase of this qubit, you can use with this one block stair. This is difference visualization of the quantum circuit. So the Q spares give you some information about the phase in the qubit, and then and the plot block space and plot multifactor give you some direction of qubit in each qubit. So okay. What about quasi probabilities of the system? So we could simulate of the result of the measurement of probability of the measurement of from the circuit is like this. So this means that in the quantum circuit A, so it's A. This one quantum circuit X, when we have dealing with the measurement, so you have got some 50-50 probability between this in the state 0, and so only like coefficient in the state vector. So maybe the previous only consider how to determine some state vector and unitary matrix. And what about when we are using QSM simulator to doing the real measurement of the quantum circuit? So this one, we change the calculate not state vector simulator but QSM. So the QSM means that we dealing with the measurement platform of the Qiskit. So sampling this means that maybe if you repeat this calculation up to maybe up to 1000 and also 100 up to you. So maybe we're dealing with the this means that we try to configure again in the qubit A. So this means that when you are using a measurement of the system, so you can add some code like measure all, which means that we have to calculate all of the measurement of each qubit. So this one, this gray color is mean that here to I think that not maybe some noise or maybe to give some limitation to doing some calculation. But when we are doing so calculate the simulator PC9 with the sampling measurement up to 1000, so we have got that the count of the measurement close enough between each other. It means that maybe there are maybe some discrepancy between 0 0 state and 1 1 state. I think it's not problem because it is appear every measurement in the quantum system. Okay, so in the measurement depends on the how many you are declare with the sampling. So if you is using 8, what about when we are using 1? This means that every you higher of the measurement, repeating measurement, the result of the count of maybe the count of the probability close enough with the theoretical.
So is that really the only way we can know the relative probability between the two bases?
Yes.
We have to do a lot of measurements.
Oh yeah.
Is that the only way? We do in performing probability. I mean, if we only measure once, can we still get the information about the relative phase?
Okay. So maybe that's right. So if you only doing one measurement, simply what happened? Only 0 0 you have got. What about 2? Only 1 1. So the first one is the fewer you are declared with the measurement, so you have not obtain some realistic result from the theoretical. So,
Try that.
But still, even if we do number of measurements to get a good statistic, what we obtain would be only the probability, right?
yes.
Not the phase. So we not need to have this information of relative phase, because in fact what we get is only relative probability. It's a real numbers, not probability. So I mean, in the true quantum state, right? If we can preserve the information very by the computer in terms of still quantum state, ideally we know the resulting quantum state, the final quantum state, in terms of basis multiplied by the relative basis, right? Like by doing this, what we obtain is merely just numbers setting probability.
Correct.
Which means that we have lost some information. I mean, by losing that information, is the information that we lose is not important, or it is
So the closing information is maybe in the give some error output. So this means that in the maybe QSM simulator, like the doing calculation in theoretical, but in this measurement only give a discrepancy between each other. So this is not a problem. But when you are using the real system, maybe I will back to initial measurement. So maybe when after this, you have to find that in the real system, not only 0 0 state and 1 1 state, but in the realistic quantum computing, we have some noise. So please got confused that there are some noise introduced in between 0, and 1, 1. So discrepancy between QP bits, the theoretical, contribute in the noise of the measurement. So this is like a statistic of head and tail in the real sector. So many you have tried, so many is probability going to one half. Okay, so big maybe 4. So maybe I am going too fast. That this is what about when you maybe you have a dealing with you have dealing with some arbitrary state, not zero state and also one state. Maybe like this one, you could declare with this mean. This mean that you have to declare with the column matrices. That A is mean in the up and one is square is into its initial state. This mean that you have taken some arbitrary state in here in the system, not zero state initially. So this arbitrary state. So what about how to get some unitary matrices? So this is unitary matrices from the arbitrary state. Because we are dealing with the qubit, so the unitary matrices give you some matrices with the size 8 times 4 times 4. So what about when we have direct to only maybe it's better. You have direct to declare some zero state. You can using like this set vector from labels 0, 0. So we could doing some mathematical operation like the involved between SV that means that we are dealing with the 0, 0 state, dealing with the so involved with the connector product with the initial state, and we have obtained that. So what about the state vector? So we have obtained that the initial state cross connector product with the 0, 0 state will give you this result. So what about rotation matrix? This means that it's only additional space. Okay, how to dealing with the unitary matrices? So unitary gates. It depends on the theta, phi. Also, there's some P with the in the qubit 1. Then what about when we involve some topology gate for CNOT control? There are some two differences. CNOTs only qubit 3 in qubit 1, but in control you can you have declared in the qubit 3 control the all qubit. So what about when control the in the Hanna market? So this means that you have you declare this Hanna market in the qubit 2. So this get a control of the Qiskit to introduce to circuit case of the explanation from the Dr. Agung. So in Agung state is so this means that in this not in this tutorial. I'll give you some three entanglements that like a fair state and reactive. So you have got some measurement only 0, 0 and 1, 1. So what about how to deal with how to simulate quantum computing into the IPF? So this is first challenging. So the participant please IPF quantum platform. So you have to register. So they get the IPF account, and you got some confirmation email after you get the IPF and IPF. So you have done maybe you have an account on the IPF quantum computing. So please copy the IPI token. So this one is how to connect with your local computer with the IPF quantum computing. Maybe just copy it into some text file or .dat file. So this is to make your IPF token is secure. This one, how to IBM IBM quantum computing. So please, if you have done, so please copy this one, IP token like this. Is maybe I'll give you some briefly. This is IBM token from IBM Blue. So I'm not give you in the jump into this one because you can fill it in the token change with your API token directly. But in the day I'm not doing it because yes to keep secure my account. So the next step is maybe I'll hide it of the API token from you. So with the to read from the IBM token right. So this is IBM token. So if you have account, please you can check with your IBM token.
That long?
What?
That very long?
Yes, that's long enough. The IBM token.
Has to be put in there.
Yes, with that. But yeah, because I have a presenter in here and I have to secure my account, so I don't give you some access. So please create some IBM quantum platform. But yeah, this is the one method to secure your IBM token. So, and override the true. This means that you can write the IPA token not only one but yeah, so on and so on. not with one conclusion. But if you don't declare this overweight true, if you first calculation, if you got some error, then you have you doing calculation next. I think maybe give you some error. You cannot access in the quantum idea. So the override is mean that okay. So this IPA token have read in the quantum IPM. So what the IPM quantum, the real system of IPM quantum computing can we access and we use it in the time. Okay, so when you try to how what quantum the real quantum computer you can access this one you can please bring backend in the Qiskit that's they are on their IBM Brisbane, IBM Kyoto, IBM Osaka. You can use it to doing some quantum system. So in this tutorial, I try to access in IBM to looking for the IBM Brisbane. You can please check this link. So you can access. When you click the IBM Brisbane, so this qubit dealing with the up to 127 qubit. So that's mean that because this IBM quantum computing dealing with the supercomputing qubit, we have some configuration of the qubit. So this means that every configuration like this can give you some error. So some error and some noises of your measurement.
So that 127 qubit is called single quantum computer that the user can use.
Yes, up to.
Okay. In fact, can you use as much? Have you used that? Yeah, many qubits.
Yes, we can use it, but yeah. And when you have a submit job in the IBM queue, you have to maybe some one patient because long enough to waiting from the calculation. Yeah. So don't worry, I will give you some alternative way to doing some noises. So, but you when you have to calculate in real system, this method is maybe is appropriate your result. But if you only yes, I only study it and I know it. Okay, no problem. I'll give you some alternative way, not waiting enough to show your calculation. Okay. Okay. After this, to call your backend using this submit job into IBM queue, and then after submit this because long enough. So I have maybe I skip it. But when you done with it, with your submitting your job into IBM quantum computing, you will see that's configuration like this. Is my calculation actually it's like 2 hours. Maybe I have to wait until 1 month. So yeah, maybe this not working when only you are studying. Okay, I'm going. So this one and you have got probabilities from the Yes or no? So, because we have to long enough to wait your calculation in real system, IBM quantum computing give you some mimicking using known as a fact provider. So, what does mean of fact provider? So, fact provider is like the your local computer can calculate some like a quantum IBM, but it's not an quantum IBM. Yeah, like your cat is alive or your cat is dead. So this one. So this means mimicking like your calculation doing it in the local computer, but the configuration like in the real system of IBM quantum computing, but your calculation not doing in IBM quantum computing. Okay. Like a GPS, you know, GPS. Okay, so because we're dealing with the IBM Princeton, there's up to 127. So I call import with the fact question that question 2. And you what kind of fact provider in the Qiskit? So you jump into the link. So you have found that there are so many backend in the quantum computing, like Upland, Belem, and Jakarta, and but this means that when you affect unlike this means that affect 27 qubit backend. So you can use it maybe Jakarta. Okay. So when you are dealing with the only the 7 qubit, you can use it Jakarta. Perfect. I don't know how, when the IBM got my my access in the IBM Yusrul. So maybe after join the summer school and after get the IBM quantum computing cut up the lower qubit like IBM future. So before this version, you can see that this one, okay, I can use the IBM future can access, but I don't know today. Maybe I and you, all of you, you can access IBM future again. So again, queues only to direct to either quantum computing. So
is it what you mean by fake provider or fake machine?
yes, this is a fake machine.
Does that mean a simulator?
What?
Is it a simulator?
Yes, this is a simulator, but mimicking with the configuration of the qubit and ring system.
Yeah. Why don't you just take off simulator?
I don't know about that. So this method I got some.
I mean, is it still useful? Well, probably for the purpose of getting the computing results in the time duration we expect. Perhaps if we have our own conventional code that works for the classical computer, we are sure that the computing time that we may estimate may still worth waiting for. Perhaps then we don't really need to do or to use this fake provider if we cannot get access to the real one, right?
Yeah.
But does it still have some usefulness in terms of just checking our quantum algorithm?
Yeah. So the
rather than just use our conventional code and classical computer, since we want to finally use the real quantum computer anyway, before we have the access to the actual quantum computer, is it that, well, it is still useful to use this fake one one, at least to make sure that our code works.
Okay.
Is that the purpose?
Yes, I think this is the purpose. So
To do debugging, right?
yeah, to do debugging. So before you submit into the realistic system in quantum computing, so the fake provider is you have get some benefit to doing your code is not bugging. Okay. So yes, I got some information of a provider from my friend in the summer school. So, because I don't have because in the summer school there are so many friends access in active Qiskit, so the queue is long enough until maybe 2 months. 2 months. So I don't have to long enough because I don't have to wait long enough because I have to submit this project. So because yeah, my friends give me some alternative way. Please, you can use paper method. This not I think it's different plot when we compare with the realistic quantum computing. Okay, so okay, maybe I for this. So when you from the Qiskit provider web, because why I'm using using the version 2, this means that we have to similar with the IPM principle dealing with the qubit. So how to calculate the quantum circuit in the Bell state. If you a little bit second, so yeah, it's mean that in the previous one. Previous one that tells that when you are using a local computer using a QNX and simulator, you only got some two state, 0 state and 1 state. But in the realistic quantum computing, you don't so some two result, but their noise appear here. So this means that in realistic quantum computing will give you some noises, not because we observe that state in the 0 and 1 not equal probability, and because there are some contribution in noise represented by the 0 and 10.
Can we distinguish? How can we distinguish between just noise and actual phase?
So when we are dealing with noise and some phase, first doing with the theoretical result first in the QIS one, and then when we calculate in the realistic system, so you have got some noise, but maybe take a note that we are using a qubit lower than the frequency, then the noise may be going to growing up. So this means that if you using higher qubit, so we can push the noise of experiment. So when maybe you can change with the IBM with Jakarta. So this maybe you can change with big Jakarta or anything else that keep it lower than the Washington. So maybe you have got some error greater than the big Washington. So but in the Qiskit runtime Qiskit, like the realistic. Maybe the developer gives some how to deal with the noises, so we can suppress the noises, noise of the system. So, but then today I'm going to give some tutorial how to.
By the way, we may expect to get noise if we use the real quantum computer,
Right.
But if you use only a simulator probably can be tuned so that it is like ideal quantum computing without noise, right? I say that using fake phone computer, the simulator, to test what should I get in my final product state. Then that information can be used to at least when we use the actual phone computer, then we can distinguish between whether the appearance of that small probability are just noise, since we didn't get that one when we use simulator. I mean, do you think that is probably the advantage of one of the advantages of the quantum simulator? At least to be able to know the ideal result, which is free of noise, before we submit our work to the actual quantum computer.
Okay. Yes. Yes. This is alright. Yes. We first need doing this in ideal cases.
Yeah, I mean, this visualization of the result, the counting that you are displaying now, this is the result of the actual quantum computer, right?
Yes. The real
Not a simulator.
Not simulator.
Okay. Because I guess if it is from a simulator, then that 6 and 20 may mean something important. Since we assume that our system shouldn't have noise, this is a simulator, right?
Correct.
If this is from actual computer, then okay, then I may believe that this is the couple.
Yes. So the noise is in the realistic quantum circuit is maybe the interesting one, because yes, this one we are jumping to give you some. This one is a computer configuration. What about when we're dealing with the quantum IC chain? So this is this is the quantum circuit of the quantum in the IC chain model. So, but this configuration only dealing with the in specific node. But in the IC chain, we are dealing with not only specific time but span of the time. This means that I will give you this. Here I'm using a picture data. It's only considered up to 7 qubit. What the results? Simulation I define some number of qubit 6. Try to calculate it in time in 1 second until 25. So I just learn. So this I give you some motivation about the noises in quantum real system. Maybe the rest of my code, please you can run it. This one. No. Maybe any question? What about the time?
I think actually the time is up. You can add 1 more hour.
I think I have. Go ahead.
At least your microphone is good.
Okay.
Yes.
I want to ask, Yamata was completed, right?
Yes.
I know it that vector or to add you add and we can use adjective, but in case of text provider, can we use GPU or
GPU. Oh, okay. In the state vector of and then unitary unitary simulator, this means that is this you are using a theoretical calculation. Not using CPU or CPU, but yeah, especially the block of money using a CPU, CPU or CPU, not CPU. Okay. In the Pet Jakarta is yes, this is what to mimicking the realistic system and the quantum computing. So this means that I don't know how define some function how to declare with this. So please remind that the effect Jakarta and maybe etc. So this code going to mimicking this configuration of the superconducting qubit like this. So the configuration of superconducting qubit give you some error too.
In provider, I learned about how it can be transferred to
Okay, so maybe I don't know how to calculate the step vector in the big provider. So as far as I know that a step vector is only provided in the theoretical calculation, but if you have access in the accurate quantum computing, so the step vector you can do it with CPU based, not CPU. So it's just like the AI and machine learning, and you choose CPU and CPU, but in the maybe in the Qiskit, the default is a CPU. So this is and ask. This is the result of the maybe this claim some type model in the IBM quantum computing based on this paper. Symbolic quantum. Result I keep reproducing from the figure this P. So why does this fact provider is an alternative way to simulate realistic system? My result is maybe dealing with the respect with the previous result. This one. So this means that in the calculation I try to do some maybe some measurement only dealing with the qubit 6, but in the spin Z direction. So this means only to because the measurement maybe lot of for measurement, but I only consider okay when you give measurement 0 picking and 1 picking. So there's a compile it in one array. So I'm doing the expectation value of the measurement, and we got some this one. So this grades mean that by the total decomposition. So this maybe it's a theoretical result, but when we're dealing with the some quantum realistic quantum model, that we have that this result that give us some noise of very badly. So so result not fit with the real ones, but yes, results from the realistic quantum. So this means that the noise of the measurement will give you some insight. Okay, we have to suppress or maybe the dealing with the number of qubit higher than 7. This is I can use a database of the 7 qubit.
One more, last question. Maybe simple question, I don't know. You said you have this experience in completing quantum computing job, right? I believe you have the code that you prepare to calculate something. But up to this tutorial, I still feel that I do not get the idea of how to construct a real calculation. For instance, how to add two numbers and translate this type of simple calculation into simple.
Okay.
How to multiply two numbers, how to do division, how to square root, so on, in terms of
okay, this is
developing the system.
okay. Okay, maybe this is a very challenging question, not only, but yeah, but more of a scientist. When you Professor Ajay said, okay, maybe we have some matrices, how to deal with this matrix with the quantum circuit. Yeah. Very what could I say that's only trial and error. So I can give you some exact results. Yeah, some of people only give the some trial and error to get okay. There's this construction of the quantum computing with the matrices. So this one is very challenging for simulating quantum computing. But yeah, maybe as far as I know, we can using a operational quantum engine solver. So maybe I will give you in the next tutorial using a penguin. This means that it's tomorrow. This is tomorrow. So we give you some penny lens. So this penny lens is based on Qiskit. This program is based on the operational quantum mechanics solver, but if we are using a operational quantum mechanics solver, we need some initial state that in quantum computing and known as ansas. So in the tomorrow tutorial, the answers I will give you some hard initialization. So they are very challenging to connect from the matrices into the quantum computing. No problem.
Professor, I think Dr. Doni found a paper like a guidance how to convert. I see. Yeah. To
some paper.
Like scientific paper. I see. Yeah. At that time, we also discussed maybe we can make like a program to generate something to be like.
I see. Okay. Well, if you have the link or the file, I'd like to have. Thank you.
Yes, because from the audience, some of the paper, we have a homework to translate the paper into general code. So the participant can use it. Today I then create it. Okay, maybe enough for today's workshop. Thank you very much for Mr. Yusrul for the for all participants to attend this workshop. And maybe as you know, this is just introduction to Qiskit. Like you can explore more if you are interested in this project. Maybe you can directly to the website, or if you still have questions, you can email Mr. Yusrul to
answer. Okay, yeah, today agenda we still have second day tomorrow. The workshop tomorrow start at 8:30. Yeah, and maybe I will close this workshop and thank you very much and see you again tomorrow to this room at 8.